So we're going to be talking about now the shape function properties in 2D. I had stated to you that we have to understand several properties that shape functions have in 2D. It's highlighted over there. First of all, why is that a shape function is 1 at its own node and it is 0 at the other two nodes? That's one thing. Shape function varies linearly along the size between its node and the other two. Shape function is 0 along the side opposite to the node, and scalar phi is related to the nodal values by a set of shape functions in linear in x and y. Alright, so let's go back and actually draw a two-dimensional finite element, and we'll go from there. So let's say we have chosen the color here, and I'm going to choose to draw a line. So from here to here, like that. And then we need to draw another line to complete this from here to, oh, it did not go too well, so I'm gonna have to erase this, but let me try again. I'm gonna go from here. Why? Draw line. I don't understand why it makes a line like that. And if it does, I'm going to try to go the other way. Over here, and we have this line maybe, like this. And then I am going to draw another line that joins this one. I'm not going close to the, yeah, there you go. So let's say this is a triangular finite element, not necessarily both sides the same, but the question is, what are the shape functions and why the shape function is equal to 1. So this is the first challenge that we have is in here. What are shape functions? So how do we understand this? What is the purpose of a shape function? What do they do? What do they mean? Okay. And then why is it 1 at a node and 0 at the other two? Okay, so let's say in here that this is I, and this is J, and this is K. There is this little Manny here, just standing in the middle of this. There it is. There's this guy. Let's make his head a little bigger. Good. He's just there. And there is one guy over here, like that, yeah, wearing a hat. This and this other one. He also, yeah, he is there. And we're gonna put a third man right there. All right. So this guy throws this this rope, a rope around him, and it passes to all the others, and he ends up being tied by this. He's also tied by this one. They're all wrapped around him. And there's one up here. Okay? We are going to call this ace of 1. This is ace of 2. And this ace of 3. Yeah. So what's happening here? This man, he cannot walk by himself. He is going to be thrown out back and forth by how strong these three guys are. Yeah? So it means that if you have, let's say, the node, let's see, the node, let's say this one, he pulls it all the way into here. So here's the, so he pulls it all the way into here. What happens to the other two areas? We are going to establish very clearly the ratio of the area A1 divided by A. This is the shape functions. Okay, this is also is a percentage of total area, right? Yeah. So let's say that this guy he has big muscles, and he is going to outdo these other two that are also holding this guy in the middle. Hopefully he doesn't get all strangled up by all these three guys pulling him. But this one, let's say he pulls it this way. Where do we have, where does where does this point come? Okay, so if he pulls over here, isn't it true that A3 is equal to A? Do you see that? If he pulls them over here, just so that you see how close he is, I'm going to do it with a dotted line. So let's just do this one. Isn't it true that it would be like this, eh? Oh, yeah. And the other one would be like this. So it describes three areas. But do you see this area, how close it is to the big area? So the conclusion is if K pulls in, why don't we just write it down? If K pulls all the way, this area is going to grow into the whole area. So So in this case, A1 is equal to A. So the ratio of A1 divided by A has to be equal to 1. This is what I'm trying to say. So if it is equal to 1, the other two, you know that the ratio A1 over A plus A2 over A plus A3 over A. What is this? This is saying that this is the total, yeah. So A1 over 2 is a percentage of this would add up to 100%. So okay, so that's the so if this is true, this ratios, this has to add up to 1. Yeah, this has to get up to 1. So how would the plot look like? Let me show you something here. I wonder if you can select and copy here. It's not start too entangled up. I'm just going to draw it again with a line. Let's do the other one. Let's do the other line. Yeah, okay, so here's, so if it is 1 at A1, which is, this is I, this is I, and this is J, and this is K. You see? If he pulls it in here, the shape function is going to be here. So this is piece of K. Okay, this is piece of K. But if that's the case, this is 1 here, and okay, and then the other one is over here, see? This wall here, if you look at from the top like this, See, it varies linearly in this. Do you see the, perhaps I make you see the figure. So you see how it varies. Varies in a line from 0 to, see, it varies a line here and varies in a line here along the vertices. And the vertex I and K and R and alright. So we have this, we have proven the second principle that the shape function varies linearly from this to the other one. So it's here from this to the other one. Okay, so we have proven that the shape function's ratios add up to 0. We also have proven that the shape function is a linear and that is aligned along the other node. So it's 1 at the node here and then 0 at the other node. And this you can see, because if you look at in here, you look from another perspective. In here, it's like it's ground zero and things are going up. So any questions about this?